The code wrapping your AI agent may matter more than the AI itself, and 2 new research papers make that case in a pretty striking way. Let's talk about what's actually driving performance in modern AI agents, because the answer might surprise you. We've been trained to think that when an agent isn't working well, the fix is a better model. Smarter, bigger, newer. But researchers from Tsinghua University and Stanford are pointing at something different: the harness. That's the orchestration layer, the scaffolding, the architecture that wraps around a language model and turns it from a static text predictor into something that can actually take actions in the world. Think of it this way. The model is like a CPU, powerful, but inert on its own. The harness is the operating system. And it turns out, the operating system is doing a lot more heavy lifting than we realized. Here's the number that stopped me. The same model, same benchmark, 2 different harnesses, and you can get up to a 6 times performance gap. Not 6%, 6 times. That's not a marginal tuning difference. That's a fundamental rethinking of where the leverage actually is. The Tsinghua team looked at what happens when you strip a harness down versus letting it grow bloated with features. A lean, stripped-down harness used 14 times less compute than the full version. We're talking about 1.2 million tokens versus 16.3 million, 51 API calls versus over 600, and it hit the same benchmark score. All that extra machinery wasn't helping. In some cases it was actively hurting. Verifiers, which intuitively sound like a great idea, actually dragged performance down. Multi-candidate search? Also a drag. The only component that consistently helped was something called self-evolution, the agent's ability to learn and adapt from its own experience. That's a really uncomfortable finding if you've been building agents by layering on features. More tools, more checks, more structure. The research suggests you might be working against yourself. Then there's the question of how you write the control logic in the first place. One of the most striking results came from taking a harness that used code-based logic and rewriting it in natural language. Same underlying logic, different representation. The result? Performance jumped from 30% to 47%. LLM calls dropped from 1,200 to 34. Runtime cut in half. The representation itself drove the gain, not a new model, not new data, just expressing the same instructions in structured natural language instead of code. The Stanford work, the DSPY paper from Omar Khattab's group, takes this even further. They built a system that automatically optimizes a harness using raw execution traces. Feed it what actually happened during a run, not a cleaned-up summary of what happened, and the system figures out how to improve the harness from there. Using that approach with Claude Haiku, one of the smaller, cheaper models, they hit number 1 on Terminal Bench, outranking systems built around much larger models with hand-engineered scaffolding. And here's the detail that really matters. A harness optimized on one model transferred successfully to 5 other models. The harness became the portable, reusable asset, not the model. You build the harness well once, and it travels across the model landscape as models improve. Which brings us to what Anthropic has been calling the subtraction principle. Every component in a harness encodes an assumption that the model can't do something on its own. But models improve. Those assumptions expire. Vercel reportedly removed 80% of their agents' tools and got better results. Mature harness engineering, it turns out, looks less like construction and more like pruning. So what does this mean practically? Before you reach for a better model next time an agent underperforms, ask yourself 4 questions. What's in the context window that doesn't actually need to be there? Which tools does the agent use rarely or badly? Are there verification loops or search components that might be hurting rather than helping? And is your control logic written in code when it could be written in plain language? Swap summaries for raw execution traces if you're building feedback loops. And be honest about which parts of your harness were compensating for weaknesses in a model you're no longer using. The uncomfortable truth is that we've been solving the wrong problem. The question was never which model to pick. It was always which structure to remove.